Before we start the scientific part, just a few practical announcements, and I'll be very quick. So here there are folders for all the registered participants, where you find some basic information in your tag. So for speakers, if you don't use Blackboard and want to use computer, we need to stick to this laptop computer. So in case we can give you a USB pen to transfer your file there. Finally, so there are two sheets here. One is just for general presence, and the other is for tomorrow's dinner. Okay, so please sign the present one, and if you want to attend the dinner, also the second one. Finally, typically speakers are filmed, okay, and you will be asked for permission to be filmed, okay. And because of the filming, typically when we ask questions, please try to use the microphone. Okay, so also the questions will be recorded. I think that's it, unless you have questions. Okay, yes. And all right, so I passed the microphone to the chairman, today's chairman.
Thank you. It's my pleasure to introduce the first speaker, Davi Maximo from UPenn. He's going to talk about Morse index estimates for minimal surfaces. Thanks.
Thank you. Thank you, the organizers, Lucio and Andrea, for, pleasure to be in Italy in the summer. It's always nice and lovely to be here. So let's see. So I want to talk about some Morse index estimates for minimal surfaces. So let me go through a couple basics. First, I recycled these slides from a talk I gave to graduate students, at least the first one. So if they're too basic, well. So minimal surfaces, they are the most basic variational problem in geometry. And I guess they really started, the theory to be developed with this question of the Plateau problem, which is if you give me a certain boundary in R3, what is the surface that spans that boundary that has the least area? So Lagrange posed that, but actually got the name of Plateau, which was this this Belgian guy that experimented with soap films. So and it's a central question in geometric analysis. It's been solved, but it's not been solved. It's the kind of problem that, if you want, it can never be solved. You can just keep, putting restrictions on the competitors that you allow, and you can, try to solve in that class, right? But as mappings has been solved in the 30s, and it also led to the development of this GMT. So I'm in Pisa, I don't have to say much about that, right? It happened right here. So with the work of Di Giorgi. But I do want to make one point, which is usually in the PDE literature, when you say minimal surface, you actually mean a minimizer of the area. But for me, it's important to make a distinction that I'm going to consider a critical point only for the area functional. Okay, so let me say that on the next slide. So here's the PDE that the minimal surface satisfied, and it's equivalent to having zero mean curvature. So throughout my talk, I just want to consider a surface in R3 with mean curvature 0. So let's say sigma in R3, so it's complete. And it's also important that sigma has no boundary, and for the purpose of this talk, let's say that it is two-sided. Okay. So what is the point here? The point is that once you are in R3, if you have zero mean curvature, there's a few ways of saying that a complete minimal surface, without boundary, has to be non-compact. Okay. But I'm gonna just leave it that, so with zero mean curvature. Okay, so let me start. So the theory really started. I mean, this is obviously as I will show in a later slide. This comes from the first variation and second variation of area, but this is actually not how this theory of minimal surface in R3 started. It started with the observation that this is 0 if and only if this map, I just look at the normal vector from sigma to S3, if this map is anti-holomorphic. And this will come out later. So anti meaning that it changes the orientation. But as for all purposes, you can think if you have a minimal surface in R3, it has a surface of, it has a complex structure, right, by just coming from the mesh of R3. So it's a Riemann surface, and the sphere of R3 with its canonical complex structure. So the mean curvature is 0 if and only if this is anti-holomorphic. So people discovered this in the 19th century and they obviously got very excited. And I guess for the first 100 years or so of minimal surface theory is focused more on this point of view, this sort of connection with complex analysis. So let's show you some examples of minimal surface in R3. So the first one is the flat tube plane. I guess I don't have to draw that one, right? Or attribute it to anyone. But the next interesting one is the catenoid, which was found by Euler, which is just like this rotationally symmetric minimal surface. So so this guy here is actually a sphere punctured with two punctures, which correspond to these ends, and so and these ends here, they have unbounded height. It grows logarithmic. Okay, so it's a catenoidal end. The other example, which is the helicoid, it's just basically you take a straight line, you have this x3 axis, you take a straight line and you just rotate it around, going up like this, you get yourself a minimal surface. And I found this picture of people attempted to recreate the helicoid with soap film. So it's highly unstable. So this is actually an awesome picture. It's very hard to do this with soap film. But, and using this connection with complex analysis, some other examples were found. So this is the Shirk surface. This is a very interesting minimal surface. Basically, it looks like two planes from a distance, right? So these are asymptotic to planes. But when you get closer to it, you see that these holes. And this is embedded, perfectly nice minimal surface. And this is the Schwarz surface. I put this name of this guy here who was Schwarz, graduate student. Apparently he played a role. So as a tribute to graduate students. So this is a minimal surface on the 3 torus actually. So it's on the lattice, but you can reflect that and you get yourself a periodic minimal surface in R3, right? So all these surfaces that on the 19th century using complex analysis, they were somehow periodic. You find some fundamental piece, you solve the Plateau problem in a certain way, and then you see that you can keep reflecting it, or you can use this Weierstrass representation which is explore this connection with complex analysis. You create some data and find yourself a minimal surface. I won't go there too much because I want to focus later on the variational side. But you see, all these minimal surfaces, they have infinite topology. For example, at least apart from the first few, right? The plane, the catenoid, and the helicoid. This one's from the 19th century found this way. They had infinite topology, and it took until 1982 for the first example with finite topology to be discovered, which is the Costa surface. So this surface, it looks like a catenoid. So these two ends here are catenoid. They grow exactly like a catenoid end grows. And this middle end is a planar end. And right in the middle here, you have a topology which you can show. You can see that this guy is actually conformal to a torus with 3 punctures. Okay? So again, he used complex analysis to do this, but it's much trickier. You have to have a nice ansatz. And later, people sort of investigating this prettier problem, they found other examples with this is the genus G Costa surface. So again, you can have two catenoidal ends and a middle planar end in any genus you like. There is the Weber-Wolf surface. It's a little more complicated. Interestingly, again, two catenoidal ends on top and the bottom, and then the middle ends are planar. Sorry? Oh, I forgot, but it's kind of impossible to just guess it from the picture. Even for Costa, it's kind of tricky to see that Costa is a torus, I find, at least, right? Because it has a neck here and a neck there. But and then the genus 1 helicoid. So this was built recently by Hoffman Weber. I think this minimal surface was one that was first discovered numerically, that you can somehow you have a surface that looks like a helicoid, but when you get closer to it, there's a little neck here somewhere. So I mean, this keeps going, right? It's no boundary, but this is really just the piece where you can see the neck. But from a distance, it just looks like the helicoid. Okay, so and now people can do the genus 1 helicoid. They can do a genus G helicoid. They can also have like a periodic genus if you want. You can see a genus here and then another one. So infinite genus, but periodic. And so there's a lot of embedded examples that can be found in the complex analysis. And I'm leaving behind the immersed examples. I have some immersed examples later, but for this, these are all embedded. So any questions so far? Yes.
Do you have Costa surfaces for all genuses?
Yes. So this construction here, you can have for any genus you want, but it's always 3 ends. And in fact, there is this big question, which if you can have more ends with all, so there was the relationship, and there is this conjecture by Antonio Ross that if you give me genus G and R ends, so the moduli space of those minimal surfaces, it's either empty or it's non-compact. Okay? So, for example, the Costa surface, it's known to be non-compact. So you can actually, and this will come up later in my talk, so this middle end here, there is a 1-parameter family starting from this guy, which basically geometrically means that you can take this middle end and you can start bending it up like this. These guys pull apart like that, and this bends up. So you have a minimal surface with 2 chitenoidal ends up and 1 down. So there's actually a 1-parameter family of Costa surfaces. Okay?
Oh, you're finished with scaling.
There is also rescaling, yes. But once you mod that out, then yes, then it's you could there's this conjecture by Ross. Okay, so which as far as I know, it's pretty much very open. But okay, so let me switch gears a little bit, which is the place that I come from. It's the variational theory. So for the first. Like I said, the first results that I showed explored a lot this connection with complex analysis, kind of leaving to the side the fact that these are variational objects. Okay, so again, the way you see that the minimal surface is variational, you just take the first variation from variable minimal surface in R3, take a compact supported vector field, you deform the surface in that direction, and here, okay, I put the formula for boundary, but let's just forget about the boundary now and look at compactly supported variation. So the only term that we have is this one. So again, to have vanishing mean curvature means exactly to have first variation identically 0. So, and following the tradition of calculus variations, once you have a critical point for a functional, we look at the second variation. So, and now I'm looking at just normal variations, and which turned out to be enough. But I have then that the second variation area, the second derivative of area at a critical point, looks like this. So it's the integral. This is the gradient with respect to the surface, and this is the second fundamental form. of the surface. So it has some analytical information here about sigma, but it also has some geometric information about, coming from the second third. Okay? So again, I can just, as usual, integrate by parts, this gradient term, and I end up with this elliptic operator L, which is the Jacobi operator of this real number Laplacian plus a squared. Okay? And we say that the Morse index, which is what I'm interested in talking right now, is exactly the number of negative eigenvalues of L. Okay? So roughly what does the Morse index means? It means that up to, so you have your minimal surface, up to a k-dimensional space, where k is the Morse index, the surface minimizes area up to second order.
Do you mean positive eigenvalues because there's vector going to minus infinity?
Oh, I mean, it's like my eigenvalue, the way that I write eigenvalue is, yes, there is always this, sorry, I write it like this. Sorry. Yes. I've just followed the elders, in minimal surface theory, at least the ones that I. But yes, but this is so writing like this, it become the negative ones. Okay, that's a good point. All right, so that's the definition of the Morse index, and so it's a natural property of sigma. So if you're doing variational theory, if you really want to see, especially if you were to construct minimal surfaces using a variational method, like Mimax, for example, or some technique from geometric measure theory, this is sort of the property that you expect to control sigma. So initially, people put a lot of focus on the topology of sigma, but you can't expect to control the topology if you use a variational method, and the reason is because all these variational methods coming from GMT, they have very weak convergence. They use very weak convergence, like very full convergence. So you never control the genus. You can have necks popping out and things like that. So but you can somehow hope to control is the index. Okay. So I see as a natural question that okay, so if the index then is controlled, let's say the index is 10, then now I can go and ask about the topology. Could the topology be very complicated? Okay, so, and it turns out to be a tricky question. I'm just going to show you the examples, which is kind of hard to guess. So the first one, the catenoid, is actually not too hard to guess that this guy has index 1, which just by looking at it, pretty much you see this direction here where if you squeeze the neck, right, you get, you decrease the area. But that's pretty much seems the only thing you can do. Okay? If I cut the catenoid in half, it's graphical. Graphs, they have minimizers, they have index 0. So if I just look at the variations here and variations here, it won't decrease the area. I have to somehow move this neck. But it turns out that you have to prove it through this eigenvalue, show that the eigenvalue problem is true. Now, the costed surface, it's a little more difficult to see, but I mean, to guess what the index of this thing is, I mean, I can see at least 3 directions, like maybe this one, this neck, there is one here in the bottom. But it turns out that this thing has index 5. So that's why I mean that it's a little complicated. And you kind of wonder where they are because, the way you define the index is basically by, it's an operator, right? The Schrodinger operator, but on a non-compact domain. So the way that you define that is basically you take very large balls, right? And you look at the Dirichlet problem in a very large balls, and then you send the radius to infinity. And if somehow the number of negative eigenvalues stabilizes, you get yourself a finite index, right? So to have finite index means then that if I cut out a large ball of a minimal surface, what I see outside shouldn't matter, right? So in fact, to have finite index means that your ends are stable. Okay? So in other words, having finite index, by definition, there is a very large radius where once you intersect with that ball of radius r, right, all the index information is inside there. Okay? So somehow, probably what this means is that this necks here, they talk to each other. I mean, there's only 3 necks, but somehow the index is not just 3. Okay? It's 5. And here's the helicoid, and it's kind of, if you think about it for a minute, you can kind of see that this guy has infinite index. And the reason is that it's periodic. So once you find a negative direction here, then you have infinitely many. But still, you have to go through that line somehow, because if you just look at half the helicoid, which means that instead of taking the whole line here and rotating, I just take a half line and I rotate that. That's a multigraph. So that is stable, has index 0 for compact supported variation. So in other words, if I move the helicoid away from this line, I'm stable. But somehow in this line I have, you know, a periodic number of directions. And this is another thing that I like about, there is another feature of this example that I like, which is, it's kind of like you should give up hope. You should give up on topology somehow, because this is, as far as minimal surfaces goes, like this is a plane, right? Like topologically, this is a very simple topology, right? But if you want to get analytical information out of topology, that's just turned out to be very tricky, because you have something that has the topology of a plane, but you can have the second fundamental form be as large as you want by just rescaling this. And also it has infinite index. So I like this example as something pointing to, okay, the index is somehow something more natural to control. All right, but here's a point. There is another reason of stating this about the helicoid, which is this result by Fisher and Colbury from the mid-80s, that turns out that the minimal surface in R3 has finite index, if and only if has finite total curvature. So this is another way of seeing, that this guy has infinite index. As a matter of fact, all the periodic minimal surfaces, right? And the way that the proof goes, it's sort of like, for this remark that I made, that somehow if you have finite index, then all your information is inside a ball of radius r. So outside, you have to have things that are stable. So the curvature has to decay there, right? So that's sort of the philosophy. But it's not a quantitative result. It's just one implies the other. Okay? Okay, so let me put then this question now, how to relate then the index to the topology. So we see that finite index implies finite total curvature, which is something that is related to topology, as I'll see. So, and it turns out that the connection is always for the Gauss map. So both can be seen through this map here, can be read off. Let me explain why. So first, the topology. So it turns out that if you have if sigma is embedded at least, or has embedded ends, then the degree of the Gauss map contains information about the topology, right? So this is the number of times. So this is basically the number of times this map N is going to wrap around, sigma is going to wrap around the sphere. Okay? Okay, but how then to relate the index to the topology? So it's a little bit more complicated, and I'm going to show you in the slide why so. Okay, so like I told you in the beginning, if a surface is minimal, if and only if the Gauss map is anti-holomorphic and Fu's conformal, right? So here I have an example of just the catenoid. So what I mean by anti-conformal, it changes the orientation, you see? But it is a conformal map. So it turns out that if I want to find about the index, right? there is this very interesting fact about the Dirichlet integral in 2 dimensions, which is that it's a conformal invariant. So, okay, so let's say that sigma comes equipped with this metric G. So this is just the metric of R3 restricted to sigma, right? So the quadratic form, which I use to compute the index, is this expression, the evolve G, like that. Yes, minus. So, but then because I have a minimal surface in R3, this thing is actually equal to, so I can write this in a sort of an intrinsic way. So minus a squared, this is equal to plus 2k, this is the Gauss curvature. Okay? So let me actually write it like that. All right? So this quadratic form, which I'm interested in calculating the index, I have this term, which is a conformal invariant, the integral of the energy in 2 dimensions. Okay? And then I have k, which is this guy is the degree of this conformal map, right? So in other words, so I can take then this metric H, which is going to be the pullback of the metric of the sphere. This is the round metric in the sphere. Okay? So when I pull back this to sigma, and I can write this quadratic form. And by conformality, I have that these are the same. Once I change from I have to transform phi as well. But you see, so this bit here times the volume form, this is conformal. And when I change the vol H to the vol G, I get exactly this. This is the Jacobian. Okay? So in other words, if I want to compute the index of a minimal surface, instead of working with this quadratic form, I can just take the Gauss map of sigma, right? Pull back to the surface. So it's going to be a metric of constant curvature on sigma. Okay? And then I basically have this eigenvalue problem. I have to find eigenvalues which are less than 2. Just have to shift this practical calculate. But there is an issue which I am throwing under the rug here, which is that this metric, this guy here, H, is actually not a Riemannian metric. And the issue are the branch points. So there are points where the derivative of the Gauss map could vanish. And there, this metric H is going to be degenerate. You see? So I'm going to have some singularities. So it's a metric of constant curvature because this guy has constant curvature, the round metric, but it has singularities that spread around sigma. So that is why computing the index turns out to be tricky, is because a priori you don't know where these points are. They could be spread out, they could talk to each other, they could be not talk to each other, right? But as far as at the metric itself, it's a very nice metric away from those points. Okay, so somehow the only hope is to kind of get an estimate, not really like to find it exactly. Okay, so we did this a few years ago. We proved that if you have a minimal surface in R3 with genus R and R ends, then you get that the index is greater or equal than 2/3 G plus R minus 1. There are some previous index bounds, but the main feature of our bound was that it was the first bound to capture R. So in other words, there were some bounds before, like the one that inspired was a bound by Antonio Ross, where he proved that index of sigma is greater or equal than 2G over 3. Okay, and the reason to get the number of ends involved is precisely this fact that the minimal surface is stable outside a ball of large radius. So, you can't just like argue by, oh, I have an end, so let me move it down a little bit. That doesn't work because the ends are stable, okay? So, so we basically, and we use that in a work of Tisk to somehow give like a quantitative version of Fischer-Kohlberg's result, which is if you have a surface of finite index, a surface has finite index if and only if it has some finite total curvature. So this here comes from our bound by just taking this and then using the fact that integral of k is equal to that formula by George Meeks, right? And you just unwrap that, you get this. And this upper bound here was a bound discovered by Tisk. So this was known since the 80s. And it comes from the fact that, upper bounds for the index, they are not usually that hard to find because once you have a finite topology, let's say genus G and R ends, you control the number of conformal structure. Basically, the space of conformal structures of that your surface can have is controlled. So somehow the index cannot be, so it's a very bad bound, in terms of like how sharp it is. But it's not very hard to get using, this, playing with the moduli of this punctured Riemann surfaces of genus G, okay? Complete. This is complete. Minimal surface in R3. Yes, no boundary. And complete. Okay. So, but in fact, our bound, I should say, because this points to what I want to talk next too, in the I guess two slides down the road. This bound here actually is true for immersed minimal surfaces. But the George Meeks formula only works for, like I wrote, only works for immersed ones, right? So this here assume embeddedness, at least of the ends. If the ends are embedded, then you get this. But the surface could be immersed. But as long as it has embedded ends, like this George Meeks puncture spheres, they have a sphere where you puncture at end points. We put like catenoidal ends. So each end itself it's embedded, but the surface, they're not parallel, so they're going to intersect. Okay, so and another application of this bound was this classification for minimal surfaces with low index. So this turns out to be an interesting question because when you are doing like this variational theory, usually you can do something about things with low index. You could see that even in the working with geodesics, right? Like how long a geodesic is minimizing, when is the first. So that kind of stuff usually has applications. So you can just plug that in our bound. So for example, if you have that index is 0, so you get a classification that sigma is a flat plane. But this follows from the work of this independent group of people, Carmel Pang, Fischer-Kohlberg, Shannon, Pogorelev, all around 1980. And for index 1, it turns out that if we have an embedded minimal surface of index 1, it has to be a multiple of the catenoid, and a multiple, what I mean is by the scaling. Okay? So this is a paper by Lopes-Ross. And for index 2, our bound basically says that this doesn't exist. So you get a gap which similar to what you have in the sphere, that if you're looking at embedded minimal surfaces in S3, this is the result that has been known since the 80s, is that the equators are the only one with index 1, then you don't have index 2, 3, or 4, but then the Clifford torus is the next one with index 5. Okay, but for R3, this we're missing, and in fact, the next known surface is the Costa, which has index 5. So it's a question of whether you can have index 3 or 4. And it turns out that recently we were able to show that if a surface of index 3 exists, then it must lie on the deformation of the costa minimal surface. So, and basically the way this works is that if you have something with index 3, you plug in our bound, it tells you that the topology is genus 1 and 3 ends. And then you look at classification of those guys. There is a classification paper by Costa, which basically says if you have that sort of topological data, then you have to be one of the surfaces in the family of the Costa minimal surface. But a very interesting question, at least from an analytical point of view, is that the index could change. So you have the Costa minimal surface, has index 5, right? You start deforming it. Maybe for a large parameter, the thing could one of the index could jump out to be a nullity, or even just disappear, right? Like an eigenfunction could weakly converge to 0 or something of that kind, right? So, we as of now we don't know whether. I like to say to others that on 3 days a week I think is true. The other 2 days I try to prove that one of those guys is going to have index 3. So, but it's still work in progress. And yeah, the interesting thing is because you see in the Costa, let me just go back a few slides. I don't like going back 4 slides, but let me tell you what happens when you deform. So when you deform, this guy starts to go up, and these 2 guys here, they start to pull apart. So you kind of wonder whether there's going to be a point when they stop talking to each other, so that they're going to, okay, I have one neck here, and one neck down. But it's as of now, at least as of yesterday, I don't know. Okay. Yes.
He classified by a holomorphic data, right? With Torah and so on.
Yes, by Weistra.
Compute directly the index by cross-Montiel.
Yes, it's very hard. So Nayatani, he, I should say his name because he was the one that proved that the index of Costa is 5, and it's a paper. It's hard. It's long, and he uses the fact that he knows what the branch points are, and he knows very well how the surface looks like, and according to him, his proof doesn't work for the deformation. So, but the Costa uniqueness result is different. So he is using that the underlying conformal structure is a torus. So he uses all these things about Weistra's functions, theta functions, a lot of those relations between theta functions and Weistra's functions, and so he goes very deep into this sort of like the theory of analytic entire functions, and it's actually a to the force kind of result, and there is no information there about it, at least not that I could find. But okay, so now I'm gonna just switch gears slightly and talk about immersed minimal surfaces. So all these results that I've been telling you, even though the index bound is still true for immersed surface, this classification, all that using embeddedness, right? So, but the thing is that this bound here, if you want to also classify the immersed minimal surfaces with low index, or if you want to have a better control of them, this bound has it's lacking important information about the surface, which is the multiplicity of the ends. So when you are dealing with an immersed minimal surface, it could have, instead of having an embedded end that looks just like a catenoid, it could have, this is an example of the Enneper surface. It's a sphere with one puncture, and at that puncture, you could have, as you approach that puncture, you could be going to infinity, with multiplicity, like more than one. So this is something with multiplicity 3. Okay, but it has index 1. So So again, it makes you wonder whether does the index also control the multiplicity or just the number of ends? Okay. And in fact, we showed that you can't control the multiplicity. So if you have a surface of genus G, and suppose that it has R ends, and they have multiplicities D1, D2, that to dr, then you have a bound like this. Okay, and in the process of proving this bound, we realized that we could do a little better than this, and that's how we got the result about Costa. Because, so if you, for example, if you consider embedded minimal surface, then dj here is equal to 1, so you get a better bound as far as the number of ends go, right? Well, you have this -5 here, which is horrible, but here you have like 4 times the number of ends. Okay, so all right, so let me, in the last 5 minutes or so, just give you an idea of how this is proven. Okay, so the idea, it uses the conformal structure of sigma. So we basically want to work with harmonic forms. So I'm gonna, so let's say this is the space of harmonic 1 forms on sigma. Well, so this is a huge space because this thing is complete non-compact, right? So you could have all sort of growth that you want, right? But obviously, for this to be relevant to the index theory, you need to work with, you need to choose forms that has some decay, right? So originally Ross he considered harmonic functions, harmonic 1 forms that were in L2. Okay? So in other words, that you could integrate. But it turns out that if I look at the conformal structure of sigma, right? So this is a surface of genus G and R ends, punctures. If I take a harmonic form that is L2, in L2 near this this puncture, then this harmonic form extends here. Okay, it has to extend. So in other words, so the dimension of this guy, so it's kind of like I didn't have the puncture. So the dimension of this is 2G. That's why you only see the genus in his theorem. So what do you do if you have a harmonic form like this? So so the point is that you take a harmonic 1 form and you basically try to create test functions out of it by taking the dual vector, okay, and looking at the coordinate functions of this dual vector. So this is like a omega dx1, omega dx2, omega dx3. Okay, so these are just the coordinates of this dual vector to this harmonic 1 form, and it turns out that this guy, let me satisfy this relation. If I try to, it's not a Jacobi, it's not going to be a Jacobi field, but it's almost. So this has the following property. So this is equal to grad omega, second fundamental form. Okay. So this is a vector equation, right? So if I look at this coordinate by coordinate, so if I look at this function, calculate the Laplacian, minus 2 times the Gauss curvature, I get equal to this guy times n1. If I do the same for this coordinate, I get this guy times n2. Okay? And moreover, Ross can classify whenever this is 0. It turns out that this is only 0 for very special harmonic one forms. This guy. So what is the philosophy then? The philosophy is take a minimal surface with finite index. Suppose that, so you want to control the index below from the topology. All right, so, but suppose that the index was small compared to the topology, right? So then, using topology, I can create, for example, following Ross, I can, for example, if I have a lot of genus, I can create many of forms like this. And in particular, I can make them orthogonal to the index if I want. Right? So that when I plug them in the, stability inequality, well, in the quadratic formula, I'm going to get a sign for that. Q is going to be greater or equal than 0 because it's orthogonal to the negative directions. Okay? So the goal is to show that when I have something like this, but you see, this guy, if I'm able to integrate this dot x omega, right? If I look at this and integrate dot x omega is a tangent vector field, n is the normal vector field. So in other words, these text functions, they're not going to be Jacobi fields, but they satisfy the integral Jacobi equation. Does that make sense? So the Jacobi equation is pointwise, right? But these guys will satisfy an integral Jacobi equation. And then the point is to show that if they satisfy the integral Jacobi equation, then you can actually prove that they have to be pointwise 0. But if they're pointwise 0, then this is 0. And Ross' lemma tells you that only very few special forms can have this, have the gradient orthogonal to the second fundamental form. So that's why in this original, in this bound here, you see, that's why you have a third, because for each form I have 3 functions. That's the reason why I get that third is there. And that -1 is because I have to kill off these forms that could be potentially be 0 here. Right? So I have to be orthogonal to the index and orthogonal to these forms that could have gradient orthogonal to the second fundamental form in order for me to actually get a contradiction. So basically, that's how the proof works. But the point is that there is this issue that which forms you can work. So there are these forms that if they are in L2, then you don't see the number of ends. In our first paper, we realized that there were many forms that were borderline L2. So we worked with those, and we were able to show that you can make this argument of an integral Jacobi field becoming a pointwise Jacobi field, and then if you work in a certain appropriate weighted space, right? And then last year we realized that we can do better. I mean, than we did when we proved this bound, which is we somehow try to find the optimal weight, the weight that really sort of milks all this information from this, and this was the weight that gives this bound. Okay, so that's kind of vague, but that's more or less the philosophy. So thank you for your attention.
Is there any question? Comments?
So what do you mean by borderline L2?
So that's a good question. So basically, there are certain one forms that, for example, a form that has a pole of order 1 at these points. Okay, so when I try to look at their L2 norm, they don't integrate. But if I put any weight on them, then they integrate. It's like this function, right? Like a 1 over x just x squared and things like that. So it's really, it doesn't integrate, but any weight, then it integrates. So we work with, we work with those.
Other questions?
Do you know any single example of a complete minimal surface for which under deformation the index actually changes?
I don't know. Yes, that's a very interesting question. I mean, the problem is that the Costa seems to be the natural first example to look at, and it's already difficult because it's a really, you're really deforming the surface, not just scaling, right? So with the plane and the catenoid, there's not, there isn't anything you can do, but Costa is really the one where you can start. I guess there could be some sort of simpler immersed cases with like a simpler topology that one could look at, but I'm not aware of those. So this is, but it's the problem. I mean, I don't know if it could be something coming from the infinite, from the essential spectrum, right? So the index could go up, or you could have some direction that goes towards the infinite spectrum. And even for, I searched the literature a little bit, even for just like shortening operators in general, like in non-compact domains, and when you have a family of potentials and so on. And I couldn't find much, like so.
What do we know about a moduli space of such it's a nice space?
So for Costa, it's a half line, right? So for Costa, once you kill, rescaling, then the moduli space is precisely a half line. So Costa starts with Costa, and there is a reflection actually. You can, instead of bend up, you can bend down, right? But there is a symmetry. But you can start with Costa and you can just deform, and it's non-compact. So, and what happens in the end is that these two necks, they pull apart. This is what is quite interesting, is because let's see. So, okay, so these two necks, they start pulling apart, right? And so you could ask, what happens if I rescale the surface so that they stay at a fixed distance to each other, right? So if I do that, if these guys pull apart, now I'm going to rescale. It's still going to be a minimum first, so that, I don't know, they're distance 1 from each other. Then you are starting to bring these catenoids down, right? Because you're rescaling, you're dividing by some big number, and the surface is going to look like this. It looks like a let's see. Let's see here. It looks like a well, you see why I use slides, right, with pictures now. But it basically, it's going to look like, okay, it's going to be embedded, but it's going to look like three planes with a neck here, and a neck there. You see, because once I bring these guys to a fixed distance, if I make this to be distance 1, let's say, then I'm bringing the catenoids down. So they will converge to a plane with 3 punctures and multiplicity 3. All right. So it's kind of, you could imagine a scenario where this has index 3 for a very large parameter, because the point where you have 1 for this neck, 1 for this neck, and 1 for that neck, and they don't talk to each other, right? Is the picture clear, the example? So I start moving in the moduli. This two necks, they come apart like this. Now what I'm going to do is I'm going to rescale this, let's say, I just divide by a large number so that now their distance gets to be 1 again. So when I do that, I'm bringing this whole catenoid down here, this whole other catenoid down, and this one up, so that this is converging to a plane with multiplicity 3. Okay? And I'm going to have a neck here, and a neck here. So, so you kind of wonder, okay, so the index, you should concentrate at those 3 pieces. Right, one here, one there, one there. So that's a pseudo proof that, I'll be happy either way. if there is an example of index 3, or if there is not in here. Or if the index is constant. If the index is constant, it's also, if the index is constant, that's also a nice feature, that of a minimal surface in R3. That would also be interesting to me. But yes.
You lose impedance, but can you compute the index there?
For the catenoid end,
changing the flux of the catenoidal ends.
For this guy?
Yes.
I don't know either. Yes, but that's interesting because the index, when you write the quadratic formula, you only need the intrinsic metric to know, because once you have the intrinsic metric, you can take that second fundamental form squared, switch it to a Gauss curvature, so you get yourself an intrinsic expression. So yes, it could be that in that case that happens, but I'm not sure.
Other questions or comments? If not, let's thank the speaker again.
Thank you.
We have half an hour coffee.
Yes.
Thinking we can resume. It's my pleasure to introduce our second speaker, Theodora Bourni, who's going to speak from University of Tennessee, Knoxville. He's going to speak about ancient pancakes.
Well, thank you very much. Well, first I want to thank Andrea and Luciano for the invitation. It's always very good to be in Pisa. Right, so my talk is on ancient pancakes. And this is joint work with Matt Langford, who is also at UTK, and Giuseppe Tinaglia, who is at King's College in London. So these are related to mean curvature flow, so let me just make a small introduction on mean curvature flow. We say that a family of immersed or embedded hypersurfaces moves by mean curvature flow if the speed follows the mean curvature vector. Okay, so this is the equation that dx dt equals to h. H is the mean curvature vector, and I will write mt for the time slices. So this is what you see at time t. Now the mean curvature flow is a gradient flow of the area, so in general it moves the surfaces in a way so that they decrease the area as fast as possible. These are the standard examples. This is a shrinking sphere, so under mean curvature flow a sphere will start shrinking and it will eventually disappear at a point. And if you take an infinite cylinder, that what will happen is that it's going to again start shrinking and it will disappear at a line. So in general, the mean curvature at some point will go to infinity, in which time you can continue the flow. In that case, we say that a singularity occurs. Now mean curvature flow has this very nice property, the avoidance principle. This says that if I start with two hypersurfaces that are disjoint at the beginning, then under the flow they would evolve and they would stay disjoint. So this immediately tells us that whenever I have a compact surface, a singularity will occur in finite time. Okay? Because if you have a compact surface, you can put it inside a sphere. You know that the sphere has to disappear at finite time, so something has to happen to the surface that is inside. Okay, we will call a solution of mean curvature flow an ancient solution if it exists for all time in the past. So in particular, when we look at the PDE, then this I interval, the time interval, should be defined from minus infinity up to some time t.
So why is a disk not a counterexample? You assume completeness, or
Sorry?
you assume completeness, or why is a disk not a counterexample?
Oh no, so we assume no boundary right here. So if you have a boundary,
Complete or?
yeah.
Complete.
And I didn't say this, also like, well, I mean, it's in the definition, we always talk about hypersurfaces here. Right. So why are we interested in ancient solutions? Because the ancient solutions model the singularities of mean curvature flow. So when you have a singularity, you want to see what is happening. What you do is a parabolic rescaling. So this is the same idea that happens at minimal surfaces when we say we zoom in at a singularity. What we get is a cone. Here what you get is an ancient solution. So you want to know what the ancient solutions look like to be able to say what the singularities look like. Now, we're going to look at convex ancient solutions because this, well, why are we interested in these guys? Because these are the singularities that appear when we look at mean convex solutions to mean curvature flow. Now, for a definition, we would say that a solution is compact or convex if each slice is compact or convex. And this is a property that is preserved under mean curvature flow. So if you start with something that is compact or convex, it will stay compact or convex. And we can always translate time. So in the case where I have a compact convex surface, then I can say that it will disappear at time 0. Okay, so also I didn't mention here that there's a theorem of Huisken that says that if you start by a convex surface, then this would the flow exists, and what will happen is that the surface would get extinct to a round point. Okay, so we know that when a singularity occurs, the surface has disappeared. Okay, so what are some examples of ancient solutions? We've already seen the shrinking sphere, which is, in particular, you can see how the radius evolves with time, and then what you get is that at time t, the sphere that you see is of radius squared of minus 2nt. The same you can do for the cylinder. The cylinder is also an ancient solution. Some other interesting solutions are minimal surfaces. Well, actually, this is interesting because it shows some connection between mean curvature flow and minimal surfaces. The minimal surfaces have mean curvature 0, so they are stationary solutions of the flow. They don't move at all. Now, some more examples are what are known as solidons. The solidon solutions, they move by the symmetries of the equation. Some examples are shrinkers, which are shrinking under the flow. This is an example is a sphere or the cylinder. Okay, it says the same shape, but it shrinks. We also have translators. These are solutions that stay exactly the same under mean curvature flow, but they have been translated. And there are rotators, which under the flow they rotate. Now these solidons, they can be described just by one slice. Because we know how they move in time, we can just study one slice, and the parabolic problem became an elliptic problem. Now, a very known example of a translating solution is the Grim Reaper. This is an example for dimension 1. The precise description of this is x goes to minus log cos x. And in time, that's why we have t. And this is a picture of the Grim Reaper moving to the right. Okay, this moves with speed 1. Now, this guy is, even though it has a nice description, it is a counterexample to many nice properties. And one of the biggest problems is this is an example of a collapsing solution. What does it mean here? It means that, you see, as I go to the right, the mean curvature is going to 0, but the biggest circle that I can put inside, it doesn't go to infinity. We say that a solution is non-collapsed when the opposite happens. Okay, a non-collapsed solution should have the property that as h goes to 0, the circle that you can put inside or outside has radius that goes to infinity. Or in other words, you must have a bound on h times this radius. Now, the Grim Reaper can be crossed by r directions. So you can have the Grim Reaper cross rk, and this is still a solution of mean curvature flow in higher dimension that is called the Grim plane. This is a solution that is convex, but is not strictly convex, okay? Because you have this zero curvature. There exist solutions that are actually convex, and this is a rotational symmetric solution, which is called a ball-solidon. So this guy, yeah, it's rotational symmetric. As you go to infinity, it looks more and more like a paraboloid, so it's like x squared. And under mean curvature flow, it translates with speed 1 upwards. So we see that there are many examples of translators, even more of ancient solutions, so it's really hard to try to classify these guys in general. So we would need somehow to start imposing some conditions. For example, there are conditions that give you rigidity of the shrinking sphere. This was a theorem of Huisken and Sinesardi that showed that in dimensions n bigger or equal than 2, under certain geometric conditions, what we get is that any mean convex compact ancient solution is a shrinking sphere. Okay. The other names is because these authors, they were able to add different kind of conditions. Right. Now, to say that, to be able to conclude that our solution is a shrinking sphere, some condition is indeed necessary because of counterexamples. So the counterexamples are the ancient ovaloids. So these guys are convex, compact, and non-collapsing. This solution was first proposed by Brian White, and it was later, the more precise description of the construction of the solution was given by Hasselhofer-Hershkovich, and even later, Angelen, Doskalopulos, and Sesum, they were able to give very precise asymptotics. This guy here at the tips looks like two ball solidons, and in the middle, it looks like a cylinder. Well, actually, very recently, the Angelen, Doskalopulos, and Sesum were able to show that this is the unique solution if you impose O1 cross ON symmetry, and moreover, they were able to prove that it's unique for all uniformly two convex surfaces, solutions. Okay, and the Choi-Brendel here is because they base their uniqueness proof for the uniformly two convex case on a very recent paper of Choi and Brendel, where they showed, they gave a proof of when can you say that a translator is, which is two convex, is rotationally symmetric. So then, Angelen, Doskalopulos, and Sesum used this result to say that these uniformly two convex are actually rotationally symmetric. Okay, then they're back to O1 cross ON symmetry. Right, now what happens in dimension n equals 1? Here we do have a complete classification. Well, what I mean a complete classification, from now on, we will assume that we have compact and convex. So what happens in dimension n equals 1? This is a theorem of Hamilton, Doskalopulos, and Sesum, where they prove that the only solution is the shrinking circle and what is known as the Angelen oval. The Angelen oval looks like this picture, and this ancient solution looks like two Grim planes, two Grim Reapers at the side, and in the middle it looks like two parallel planes. Again, here this we cannot classify this in general. We have to say, well, I also always assume that things are embedded, and here you have to impose this because there are examples of Albrecht and Langer that they show that this, what is called a spirograph, something that, I think you have to make it symmetric. Anyway, and there is numerical evidence given by Angelen that shows that convexity is also necessary. Okay, so here's an example looks like a spiral. Right. So the question is, what happens? Can we have something that looks like the angular oval in higher dimensions? So can we have a solution? What will happen to two parallel lines? It will come two parallel planes. And the moment we're gonna restrict a solution to be between two parallel planes, it will have to be again collapsing. Okay, so we cannot fall in the previous theorem of the, I put it down here. So the ovaloids are always non-collapsing. Okay, so what happens when we consider collapsing solutions? Right. So before I address this question, I want to give you a more precise description of this angular oval because we're going to be using it a lot. Okay. So the angular oval, we have an explicit equation for the angular oval given by this cosine x equals e to the t hyperbolic cosine y. As I said, it looks like two Grim Reapers and two parallel lines in the middle. So this is given here. You see when you take y very large and negative, what you see is something very, very close to the Grim Reaper. And how can one construct this example? Well, actually, how it was found is by the evolution of the curvature. So here, in dimension n equals 1, you can write a very nice equation of the curvature under mean curvature flow. And what you get is that this expression here, kappa squared, equals the thing on the right-hand side. So kappa is very, very close to cosine theta, which is the curvature of the Grim Reaper. This is what you get for the curvature, and because you have a closed convex curve, you can describe your curve you can precisely describe your curve by the curvature. Right. Okay, so I will always consider curves which are parametrized by a turning angle. Okay, so this theta is the angle that the tangent makes with the x-axis. Right, and another thing we'll be using is that this angular oval, if you look at it at a time t, you can consider this the small length and the big length, which are called like h and l. H goes to pi over 2. This is because the Grim Reaper that moves by speed 1 lies in a slab of width pi, and L goes like time. Okay, so the big length is equal to time. Right. So how are we going to construct what we call an ancient pancake? So a solution that is collapsing in 2 dimensions, or in general like in higher dimensions, but we just stick with 2 dimensions for this talk because it's easier to describe things, is as follows. So given R, remember I said that the length is equal to the time. Okay, time is negative, so that's why I put t equals minus r. I look at the angular oval at that time, and I'm going to rotate it around the x-axis. This will create a 2-dimensional surface, which we call sigma r, that lies between 2 parallel planes. Then we take the surface, and we apply mean curvature flow. So this is a nice convex compact surface, so it would get extinct at a round point in finite time. Now, as I take bigger and bigger r, we hope that the time that it takes to get extinct will go to infinity. And if we can get uniform estimates on the curvature, then we will be able to take a limit as r goes to infinity and therefore get an ancient solution. So this is what I'll try to explain. And this construction does work in any dimension if you assume rotational symmetry, because it's not very hard once you do the 2-dimensional thing to do the higher dimensional. And what we'll do is we show very precise description of this object, which will allow us to use the Alexander reflection principle to show that this is unique. Okay, now in what sense is unique? it's in this theorem. So this is the theorem I'm going to describe. So what we have is that up to rigid motions and parabolic rescaling, there exists a unique, compact, convex, rotational, symmetric, ancient solution of mean curvature flow that lies in a slab. Okay? And as I said, lying in a slab immediately makes it collapse. So this picture, I hope you can see what is happening. Okay, this guy lies between two parallel planes. It looks like a rotated angular oval, and it shrinks to a point. And as I said, yeah, the key to prove uniqueness is to get precise estimates, which is the estimates are here. Okay, this so the slide is a bit packed, but the whole idea to prove uniqueness is if you look at these points, this would be the PT would denote the maximum height, and QT would denote the maximum length. So we want to describe exactly how these points PT and QT move. And what we will show is that the minimum of the curvature happens at the point PT, the maximum of the curvature happens at the point QT, and estimating these curvatures would give you a description of how these 2 points move. What we get at the end is that the point PT is moving towards pi/2, and the point QT is like t plus log of t. Okay? So remember, the angular oval, the corresponding point was moving like time, but now what happens? You're moving by mean curvature flow, right? So the mean curvature here should be the mean curvature of the Grim Reaper plus 1 over the radius, which is given by the rotational symmetry. Okay, so the mean curvature is very, very close to that of the Grim Reaper, but a little bit bigger, which makes this log of t appearing there. Right, and of course, like we have to, when we say like, we have to here restrict to a slab because we don't put that there this rescaling, right? When you have a solution, you can rescale it, then you get a solution at a different slab, but then we'll have a different speed. Right, and for this solution, we have to also to prove uniqueness, we also need to know the precise asymptotics, which also you can see them here by the estimates. What happened as we go to minus infinity? So as we want to see how the shape looks like way back, what happens is that this would look more and more like a Grim plane now, because the one curvature goes, so this will become almost like a line. And here I'm going to see the Grim Reaper. And inside I'm converging to 2 parallel planes. Okay. So let me try to explain a little bit why we get, once you have the precise asymptotics, why you get uniqueness. Right, so the existence will be described later. And recall that the estimates that we want for P and Q is that P goes to pi/2 and Q goes like T plus log of T. Now, what we can show is that this limit, so if I take the length and I subtract this T plus log T, this limit exists. And for the constructed solution, we will show that it's actually finite. In general, it might be infinite. But once you've done this, you can do the following. So imagine like sigma T0 here would be the constructed solution for which we know how this tip moves. We know this Qt minus this T plus log T, it doesn't go to infinity. And assume you have another solution for which this limit exists. Maybe it's infinite, but without loss of generality, we can assume that it's bigger than this guy. What we do is that we reflect this sigma T0 around this. I have a picture. Okay, so we can take this sigma T0, the constructed solution, and reflect it about an axis which is a bit higher than the y-axis. Now this reflected part, because of the asymptotics, would be disjoint from what I call like here sigma T minus. This is whatever I see below the the x less or equal than 0. So since they're gonna be disjoint for t going to minus infinity, this should be minus infinity, then the maximum principle tells me that they will be disjoint for all times forward. Okay, you cannot have a first point of intersection. So, but this you did, a here was arbitrary, so you can start putting a going to 0, and this tells me that the sigma t 0, the reflected part, lies above sigma t minus. Okay, you do this on the other side, you get that the one solution is inside the other, but this can never happen because they get extincted at the same time. Okay, by the avoidance principle. So this, this is a way how can one use this precise description of the solution and the Alexander reflection principle to get uniqueness. Okay. Now, okay. Actually, are there any questions? Probably. Okay, so let's look at the existence. So here's the figure again of a slice of the angular oval. And this is a guy that we rotate around the axis x. So rotating it constructs a surface which we call sigma r. And as I mentioned, we're going to flow it by mean curvature flow and get this family sigma rt. Okay, this is the motion of sigma r by mean curvature flow. Now, mean curvature flow preserves symmetry. So since we started by something that is rotationally symmetric, every slice would also be rotationally symmetric around the x-axis. So every slice sigma rt is a rotated curve, which we call gamma rt. Right? Now this gamma rt is not the angular oval. Why? Because if you look at the evolution of this gamma rt, is not by curvature, but it is by curvature plus a little bit. Okay? So these are surfaces that are rotationally symmetric. So when you compute the mean curvature, you can write it as you can see what it tells you about the curve, right? So the mean curvature of the rotated surface is exactly kappa plus lambda. What is lambda? Is this quantity. Okay, so this is the normal dot E2 over position plus E2. Okay, so this is, I guess, like also in differential geometry, how you learn to compute the mean curvature of a surface of revolution. Now this quantity lambda, it seems that it's becoming really bad when y goes to 0, but as y goes to 0, this guy goes to 0 as well, and you can actually show that this is bounded. It's bounded by what? It's bounded by the curvature, okay? So this is the same like derivative over position. Okay, so what happened now is that we had a two-dimensional problem, the mean curvature flow, and we can write it as a one-dimensional problem, which is very close to one-dimensional mean curvature flow. Right, so now if we look at this one-dimensional mean curvature flow, which is known as curve shortening flow, in general, well, when we have curve shortening flow, it is known that if you have critical points of the curvature, then the number of them cannot go up. Here we cannot apply immediately this, but we can do a maximum principle to show that the minimum of the mean curvature occurs at this point and the maximum of the mean curvature occurs at that point. Moreover, you can do maximum principle in the quantities kappa, well, the derivative of kappa along this part, and the derivative of lambda along this part. So you can show that kappa increases along this part, and and lambda decreases. So here, this is what this says. Lambda here is less than 1 over L. L is the L is this big distance, h is a small distance. Okay? So forget about this for a second. So lambda is less than 1 over L because 1 over L is its value at that point. Okay? So you can bound lambda by this, and moreover you can bound it by kappa. This is also these are all maximum principle. Okay, you can like take all these quantities, do maximum principle, and since it's true at the slice at the beginning, it's gonna be true later on. Right, now these quantities, the max of h, the min of h, L and h, are very nicely there are relations between them. Okay, now L of t moves by the maximum of the curvature, this by the equation. H of t moves by the minimum of the curvature, and moreover h and L are you can bound the product because of convexity. AT here is the area that I have inside here. Okay, so you can put a rectangle around, a rhombus inside, and bound h times L. Okay, by the area. Now, how is the area related to the curvature? We know the evolution of the area. The evolution of the area is equal to the integral of the speed. So when you plug in here, the integral of the speed, the first part, just kappa, will give you 2 pi, and we have this extra bit lambda. Okay, so this is with respect to arc length, and here is when I look at the parametrization with respect to the turning angle. Okay, so in curve shortening flow, you don't have this part, so you just get 2 pi here. So you know exactly how the area evolves. Right? So here we need to estimate this lambda term if you want to say anything about the area. All right, and now looking at this equation, at these 2 equations, as I said, by the maximum principle, lambda can be bounded by kappa, so we have a very first rough estimate for the area. Now the other 4, L, H, and the mean curvature, mean and max, so these are 4 quantities that if now you're able to bound one, you can bound all 4 of them. And the one we can bound, well, the one that was the easiest to bound, it turned out to be H min. Okay, and I'll describe this estimate. Okay, now how can you bound H min by these 2 radii? Is again with the maximum principle, but now it's a more geometric maximum principle. So here's your this is the proof why one can do this. So this is part of our solution. P and Q was what I called before PT, QT. And because I have the minimum of H appearing at this point P, whenever I put a circle that doesn't cross Q, the curvature at P should be smaller than the curvature of this circle. Right? Now, the curvature of this circle is 1 over the radius, so I can bound now my H min by the radius of this circle. And okay, there's this 2 because I think I'm mixing like kappa and H. Okay, but you see, because of the rotation symmetry, once you bound kappa, then you bound H, because remember H is like kappa plus lambda, which is bounded by 2 kappa. So kappa is the difficult quantity. Right, so you do a little bit of geometry here to get an estimate for the radius, and at the end what you get is that the minimum of H is bounded above by, well, here 8, you can, if you forget about this guy, it's bounded by 1 over L squared. Remember, L goes like time, so the minimum of the curvature is bounded by 1 over time squared. Okay, now also we had this estimate that L times H, because of the area, goes like T, and this, if you plug this in the previous line, you could solve this equation, you get that this H, the width, it goes to pi over 2, you already have a good estimate how does it go to pi over 2. And also again using back like this guy, you get an estimate for L and for H max, okay, because this is the speed of L. Right, so what do we have now? This gamma R is the solution, the solution of curve shortening, well not curve shortening flow, this new flow which is kappa plus lambda, very close to curve shortening flow, starting by the angular oval at, with diameter R, okay? Now I'm putting this R because I want to take a limit as R goes to infinity. We have this width guy like HR and the height LR. And remember we already have some estimates for these quantities. So the estimate for the minimum curvature, we have a rate of how H goes to pi over 2 and a bound for the maximum of H. Now all these constant C's, they have nothing to do with R. They're independent of R, so they work for any initial data. And therefore, we can take a limit as R goes to infinity. Okay, so the curvature is bounded independent of R. We can take a limit. What we're going to see is a mean curvature flow. Then you have to make sure that you didn't get the two parallel lines and that your solution is ancient. But since L, we have an estimate for L, again uniform in R, and the time goes to infinity, what we get is a compact ancient solution. Okay? And the last thing is to notice that what we get is something that lies exactly in a slab of width pi. Okay, so we didn't get something smaller. So this shows that we can get a solution, get an ancient solution that lives in a slab and in no smaller slab. Now, it turned out that these estimates here, they are not good enough to prove the uniqueness. Okay, you need something better. Yeah. And again, I'll try to say a little bit of how one can get even better estimates. Now we just look at any ancient solution of this one-dimensional flow, which is close to curve shortening flow. Okay, it moves by kappa plus lambda, and lambda is this quantity that comes from what the extra part you get when you look at the mean curvature of the rotational symmetric curve. Right, so the first thing to do is see that what you get is your asymptotics. So this gamma I is looking at this part of the curve. Okay, so you look at a time slice t, you take this part and you put it at 0, and you take a limit as t goes to minus infinity to see how the end looks like. It's not very hard to see that when you do this, what you're going to get is a solution whose curvature doesn't depend on time. So it must be a translating solution. And because we only have one, which is the Grim Reaper, it therefore has to be the Grim Reaper. However, if you don't say anything about the size of the curvature, then you can end up getting a scaled Grim Reaper. So you have to make sure that this Grim Reaper that you get is the one that moves with speed 1. Okay, so in general, you might get a smaller one. So that's why there's this alpha there to make sure we consider that case as well. So we get a limit. Alpha might be less or equal than 1. It cannot be bigger than 1 because it lies in a slab. It can be just smaller. And we want to show that alpha equals 1. Now the way one can see that alpha equals 1 is by looking at the area estimate. Okay? Why? Because remember this. Well, actually, first you can see that this alpha is determined by the maximum of the curvature as you go to minus infinity. So this alpha would be the limit of the curvature at the tip. So if this limit is 1 over alpha, then L, which moves by its speed is this maximum curvature, should be bigger than this number. Okay, so not just going to be minus t, but it's going to be minus t over alpha, which already should tell you that something is wrong. Why? Because the principal term should move differently than that of the Grim Reaper. So you go to your area estimate, and you can see that if this L is bigger than t, then you contradict the fact that your area should be going like, you contradict the coefficient that is in front of t in the area. Okay? Right. Well, maybe I'm not going to go into the details over here. Okay, so back to the proof of uniqueness. Remember, this was like a slide that appeared earlier, that we need to have precise description of how the points P and Q move to be able to do the Alexander reflection principle, okay? So you need, you need to converge to these two lines, and you need to be able to say how the tips move. Okay, well, maybe I didn't say this before, but so the biggest problem here to apply the Alexander principle is to make sure that you don't have two tips that, that go like this as you go back in time. Right, so how to get these more precise estimates? So now we know that this is what happens at the tip. We know that the tip converges to the honest Grim Reaper, the one that moves with speed 1. And we want to get these estimates for P and Q. Okay, for P we already have something, but not as good, but still. And for Q we just, remember we had that it's bounded by a constant times t. Well, and then once we had this, it's bounded by t, but you don't know the lower order terms. Okay, so just with the asymptotics of what we've seen so far, we just know what happens to the first order term. So we know that L goes like t. We know that P converges to pi over 2. Right, now, so a very useful thing is this Hamilton's Harnack inequality that says that if you have an ancient solution, then the mean curvature is monotonic, and it's going to increase. So when you go back at infinity, the mean curvature becomes cosine theta, which is that of the green plane, and therefore h is always bigger than cosine theta. This is when you look at things by, you parameterize things by turning angle. This is what this theta looks like. And recall this estimate that we had, that the minimum of the curvature is bounded by a constant over t squared, which gives us a rate of convergence of the point pt to pi over 2. Okay, that's of order 1 over t. Right, now, okay, the way to get better estimates is to try to get something better for lambda. Remember at the beginning, I said that this lambda, which is what messes up with the flow, right? It's not curve sorting flow anymore. I said that it's bounded by kappa, and I also said that it's bounded by its value at the top part, which is 1 over L. But this is not enough. We need to investigate a little bit better this term. And what happens is that one looks at this evolution of the area, right? It's the integral of kappa plus lambda. And you can observe that this lambda part is given by 1 over u. Okay? So this u is a graph. If you look at this part up there as a graph of a function, you call this function u, then you can write this integral of lambda as integral of 1 over u. Okay? Why? Because we have this this estimate, right? So it's the same. If you stare at the term, you would see that the extra thing you get is the term that allows you to go from something on the graph to something downstairs. Okay? This was actually this parameterization of the curve like this. This way and that way was used a lot in this paper by Angel, Daskalopoulos, and Sessom to show the precise asymptotics for the ovaloids. Right, so you do this and you see that this function u, you can, because the curve satisfies a certain flow, U also satisfies a nice equation, which is du dt equals kappa plus lambda over cosine theta. Okay, this cosine theta, again, it's because of this. Right, and this guy, because remember kappa plus lambda is always is the mean curvature of the rotated guy, which is bigger than cosine theta. So this u, the du dt is at least 1. Okay, so then you can integrate between two times, take a time capital T when u has reached, above some x, when u has reached 0. So you know that ht is exactly x, and integrate between t and capital T, and you get that u is bigger than minus t minus a term, okay, that you depends on x. Now this might seem irrelevant, but this estimate here, estimating u and not just h, as we've done before, is what the intermediate step you need to be able to make an iteration argument that will improve your estimate. So remember how I said that we can estimate the minimum of h is by putting the largest possible circle, which is a circle that passes through the point P and the point Q. You can play the same game now, but it doesn't have to be this point. You can take any intermediate point, right? For which you have some estimate. So you do this, and it's an iteration argument to show that your estimates improve. Okay, so now the k, you can make it as big as you want. So you have proved now that the minimum curvature is not just 1 over t squared, but it's 1 over t to whatever power you want. Of course, the c depends on the power, right? So you can power. Right, this improves the estimate on the width, the small h. Right, and all, I don't wanna, well, I guess I was ready to take that. Right, this gives you a better estimate for whatever we consider so far. Okay, it gives you a better estimate for the integral of lambda, and this estimate now, the integral of lambda, you get like 1 over t, and you know exactly what is happening at the lower order terms. So your area is exactly t plus log of t, okay, area over 2 pi. But the area should be like h width times height, okay, by convexity. So this area estimate, knowing that the area over 2 pi is like t plus log of t, allows you to get an estimate for L. Okay, and I'm just like, because I didn't want to lie, you don't get exactly what you want. You need a bit of another maximum principle to be able to say that your L has a certain, so the second order term is log of t, and therefore like this L minus this term is decreased. Right, and this is the estimate we wanted, and now you can use your Alexander refraction principle to prove the unique. Okay. Right, so this was the main steps of the proof, and let me just, the last thing I want to say is what are some further things we wanna look at. So in general, it would be interesting to try to classify any compact convex ancient solution in a slab. So far, what we can say is that the example we constructed is the only that is rotation symmetric. But there should be different solutions as well. So what we're interested to construct is now solutions that have discrete symmetries. So, well, it seems like very likely that there are solutions that as you go back to minus infinity, you don't just see something rotation symmetric, but you see something, for example, that looks like a triangle. Okay, so of course, like in any compact set, again you see like two planes, but when you take points and translate them to 0 and you let t go to minus infinity, you should either see green plane or something else. Now what is this something else? It's a convex translator that lies in a slab. Okay? So that's why it's important to know what are the convex translators that lie in a slab. And these this actually they have been studied a lot this year. First, it was Xuzhou Wang. He was the one who is given the existence of this guy. And actually, I forgot to say, he also, in his paper, he was the first to show that these collapsing ancient solutions exist as well. The first, as far as I know, that the guy that we constructed actually does exist. So he has a way to prove existence. But what was not known is that do you have existence every slab? And the same question comes up for the translators, which are interesting because of this thing, right? And it turns out that if you have a slab here of length alpha bigger than pi over 2, then you can construct a translator that is asymptotic here to the green plane, and the angle here, theta, satisfies cosine theta equals 1 over alpha, right? So let me write here alpha. Alpha is bigger than pi over 2, and here, alpha over pi over 2, right? Well, like imagine pi over 2 is 1 here. Right, so this is something less than 1. Okay, so you can do all the angles here. So it's not just a triangle. You can, have any other polygon as you go back to infinity. Right, and so there are these papers by Sprague and Shao who showed this asymptotics of these solutions for any slab bigger than pi over 2. We have worked on this as well, showing existence on every slab that is bigger than pi over 2. And in a recent paper of Hoffman, Illman, and Martin and White, they also do the existence. And they moreover show that these solutions are unique. Okay. Right. However, if you try to do now, we're trying to do exactly the same program that we did to construct these kinds of solutions, but we still don't know exactly the second order term of this guy. Okay, so because of the angle, you know that if this is alpha, this is, constant times alpha, but what is happening later? So you need one more term, which we need to figure out. Right, and another question is what happens if you don't assume any symmetry? So can you find something, can you perturb a little bit this rotation symmetric solution, get something that is not rotation symmetric? Or it doesn't have to be a little bit, something that doesn't fall in these categories. And of course, like the other thing we are interested in looking at is what happens if your solution is non-compact. Okay, so what are these, what does these guys look like? Okay, I'll stop here. Thank you.
Questions or comments?
Yeah, it's not exactly about your solutions, but I'd like to remember the story of the in R3 this translating solution, which is quadratic at infinity, right?
The ball.
Huh?
The ball solid.
What's the name?
The ball, like a ball, because I guess it looks like a ball.
Yeah, but it's like a parabola, right?
Yeah, it's x squared.
Yes, but it's not a parabola.
Yeah.
And it's of revolution. So the existence was it easy to prove the existence of a guy like this, or maybe?
Yeah, because you get like an equation.
Yes.
Yeah.
Sure. So then the key point was to prove that any quadratic guy like this translating should be of revolution, right? I think that was the open problem for some time.
If it is convex, right? Because there
convex.
are
Convex.
Yeah. But then okay, there was this. If everything is rotation symmetric.
No, the point was to prove it that it had to be rotationally symmetric, and I think now this is known, right?
And then, yeah, this was like by Xuzha Wang, right, also.
Okay, so this is a result of Xuzha Wang. Was it correct, the proof, or?
Oh, yeah. It's like a paper in the annals, right?
I think the first.
It took a while to check, right?
It took a while to check, but I mean, I also, that's why it took me a while to read the paper, because everybody was saying it was really hard, but I thought it wasn't like
So,
the worst.
at the end, it's correct, that first paper, yeah.
As far as I know, yeah. Yeah.
So then it's unique. There is a unique one after the. This.
In higher dimension, his paper produces no radial example.
Oh yes.
Dimension bigger than 3.
Yeah, exactly.
Ah, oh, I see. I forgot. I see.
In 2 is correct.
Yeah, in 2, No, Xuzha Wang, he shows that in n equals 2, this is the, yeah.
What does it mean in n equals to a surface? In R3?
Surface,
In R3 must be of revolution.
dimension bigger than 3.
It's not true.
So dimension, the hypersurface.
Yeah. Other questions?
Yeah, I was also wondering whether one could imagine something which would say zigzag, possibly. I mean, something periodic with these green vapors coming from both sides.
Yeah, so there are examples like this. I forget now by whom, but there is this example which is like the Grim Reaper and the Grim Reaper and the Grim Reaper. And I think like this one lives forever in the past and the future. But I forget, maybe it's Angen, but I'm not sure.
And I was also wondering whether there are similar examples for Ricci flow.
Oh, actually, sorry, I was trying to remember. It was last week I saw Angenet's talk, and he had a student who constructed stuff that were not also symmetric. You know, like you could put like, say a little bit here and then here more, and like they were immersed though. They would intersect themselves. Call it like the trombones or something.
And anything similar for Ricci flow?
Oh, I don't know actually. I don't know. Like this.
I mean, not like those, but like those ancient solutions with different behaviors.
Yeah, I don't know much. Yeah.
In 2D, I think yes. For the Yarn flow 2D.
For the Ricci flow.
Yeah. 2D, I think that Totti, Dascalopoulos, and Manuel Delgino constructed ancient solutions.
But they're like non-collapse, right?
Yeah, because for Ricci flow. Yeah.
But I don't know what is happening with this. I don't know what's the collapse condition thing was.
Okay, thanks.
Other questions? Theodora again.